Alright, so today I just wanted to go over some of the notes that I'd made on Heterogeneous Parallel Computing, which is a Coursera course that is currently running. So the course is focused around building programs for GPUs. And one of the interesting things about GPUs is that they are designed for high throughput. And what I mean by that is they can execute a lot of instructions, but they don't really have very sophisticated controls. So they've got something called, it's called SIMD, Simple Instructions, Multiple Data. So because of that, they have small caches. Now the idea of that is that they're trying to reduce traffic to DRAM when multiple threads use the same bits of data. So that's the main purpose of caches in that sense. And they don't generally have branching like a CPU would, and a CPU generally has large caches because accessing main memory is incredibly time consuming. So when you are utilizing a typical von Neumann machine, it's often better to have a very large cache as close as possible to your CPU, actually physically close to your CPU, so that you can quickly access things. And also, if you're really, a CPU is sort of like the general purpose computation unit. It's very good at calculating, but it's pretty much restrained to doing one thing at a time. So that can lead to a lot of bottlenecks, especially say you want to add a certain number to a million vectors. A CPU isn't optimized for that task. A CPU's, or what NVIDIA CUDA calls it, a host. The host isn't really optimized for that because the bottleneck is it has to calculate one each time, whereas a GPU has a lot of smaller cores that don't really have the sort of crappy ALUs. They kind of don't have anywhere near the rich set of controls that a CPU has, but they can do a lot of trivial, or in some cases not trivial, but a lot of simpler tasks a lot quicker. So you can have a massive amount of computation happening, even if it's not really complex computation. However, the one downside to this is if you're working with small data, it can actually take a lot more time to transfer that data to the GPU and transfer it back than to just program it on the CPU, because there is the cost of data transfer, which is actually quite expensive. But if you've got a lot of data going through, it's actually it's quite useful. And that's sort of what I got from the first part of those notes. In addition to that, there are also people that actually program something like a vector addition. Now, one of the interesting bits is understanding how CUDA works. And so essentially what CUDA does is it has sort of its C-like namespace in front of a whole bunch of things like CUDA malloc, CUDA memcopy, and CUDA free. So if you remember the C memory model, we have malloc which stands for memory allocation, memcopy, which stands for memory copy, and free, which stands for freeing pointers to things. So essentially you just place CUDA in front of that and you can just malloc things of certain sizes. And then the interesting thing with CUDA memcopy is it has an additional parameter, which is which way you're going to copy it. You can copy things to the host and then back to the device. So in this example here, I have the H_A, H_B, H_ standing for host. This is what I got from the notes. You should check out the course, by the way, Heterogeneous Parallel Programming. It's on Coursera.org. And then int n, which is just the limiting size. And that was pretty much all you needed to do for that. So in terms of memory model, it's very simple. Things on the host that need to be copied to the device. It's desc source, as it always is, so you copy things to the device from the host, from CUDA memcopy host to device. Now, if you're not really familiar with malloc memcopy, you should really know that before you start messing around with CUDA, because CUDA sort of assumes you know everything from C. So pick up KNRC or something like that. But then after that, I actually found this reasonably trivial. You're just mallocing as you would normally malloc, except this is on the device now, and you're just doing memcopies as you normally would with an additional direction to the device, which is your GPU, or back to the host. So you do your computation with this, you've made some space on the device using this malloc, which is the same size as the host. You've transferred the host code to that device. So mem copy host to device, and now it's on the device. And we do the same for B, and then later on, so in this case we're adding two vectors, and we're storing the result in D_C. So we're allocating that there, we do the computation, and then we come, which I'll show in a sec, and then we come back and then we copy to the host from the device the result, and then we just free everything on the device, which is really cool. It's very simple and quite intuitive. Now, in terms of how you actually make a program that will do the vector addition, I'm obviously not going to give away the solution to it, but these are slides from the actual lecture. Adding something is quite simple. So you've got to get the thread ID plus the block dimension times the block ID. So how NVIDIA CUDA works is it separates things into a whole bunch of grids and then a whole bunch of blocks, and then there's just some integer number associated with every thread, and we actually want to find out which integer that is. So it's just, think of it as just a continuous line of integers, 0, 1, 2, 3, 4, 5, 6, 7, 8. But we have our blocks separated into certain groupings, say of 256. So to actually find the thread that we currently have, getting the thread IDX plus the block dimension plus the block IDX will give us the integer that we can associate with each one of the arrays. So in this case, we're putting in CI is equal to AI plus BI, which is essentially saying store the result of the addition of this A element and this specific B element, which are identical, which are matching. If you imagine there's n A elements, n B elements, and you put them on top of each other, each thread is assigned one of these. So A0, B0, C0, so it's going get A0, B0, and then it's just adding them together into C0. And then once it does all of that, it returns and it's done. So in this example, we're using a grid of 256, 256, and we're adding it using this funky notation. So in C++, you use double angle brackets to represent templates. In CUDA, you use this triple angle notation to specify the dimension of the grid, the dimension of the block, which we specify here, and then we pass in what we're working on, which is exactly as you would expect: device A, device B, and device C. Interestingly, there's a few other things. So these device global host, device global on host, so underscore underscore device underscore 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 global underscore underscore and underscore underscore host underscore underscore, each represent certain keywords, preprocessor keywords that mean different things. So underscore underscore device underscore underscore works on some float function, so it returns a float with void arguments or whatever arguments, and it's executed on the device and it's called from the device. Underscore underscore global underscore underscore on some void function is executed on the device and called on the host. Underscore underscore host underscore underscore is called, executed on the host and called from the host. Why would you have a host one? Since the compiler defaults to that, because device and host can be used together. So you can have something that can be both called on the device and called on the host, and executed either on the device and or on the host. So in this case, all we're really doing is sort of something as a functional programmer. It makes a lot more sense to me because I'm used to working with just a specific case. So really, if you assume you've got some A, B, and C, and then for any I, it's really just for any I do this. Now, interestingly enough, you can assert too many threads to the actual size of the elements. So say we have 200 elements and we have like 256 threads, then obviously we're trying to utilize threads that don't map to the amount of things we actually have. So we need to have a condition here to say, hey, make sure that we're actually within our bounds. But doing bounds checking is pretty common. Besides that, that's pretty much everything I learned. There was a fair bit more. yeah, a few things that I should note is mem copies are asynchronous, which is nice. It won't block, so you can do several mem copies and assume everything will work out fine, which is very good. And the interesting thing there is if you're malloc something and you call a mem copy, it's just going to jump on, or if you're doing some sort of computation directly underneath it, it'll just continue on, which is very useful because in practice the copying is a large component for some datasets, but if you have a very big dataset, it's not a really big issue, but it is good that your program won't be blocked by that. And that's about everything I learned. I just thought I'd post a video.